Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 6 exam for February-March 2024. So let's get started. Question 1 says a student determines the mass of a meter rule by a balancing method. He is using apparatus shown in figure 1.1. Part A says as the student places a circular load on the meter rule shown in figure 1.2. Determine the distance d of the center of the load from the zero end of the ruler as shown in figure 1.2. Figure 1.2 is not to scale, so you are not required to measure on the diagram. You will just use the scale drawn on the image. So we have here at the edge is 26.5 and on the other edge is 29.5, and the center will be the average of these two values. So we add 26.5 plus 29.5 and then we divide by the number of readings, which is 2. That would give an answer of 28.0 centimeters. Part BI says the student adjusts the position of the meter ruler on the pivot until the meter ruler is as near as possible to being balanced. Describe a technique for ensuring that the ruler is as near as possible to being balanced. So we can adjust the position of the rule so it just tips clockwise and take a reading, and then anti-clockwise to get the average position. Part I says the student finds that the ruler is as near as possible to being balanced when the pivot is at the 47.6 centimeter mark. Calculate the distance A of the center of the load from the 50 centimeter mark as shown in figure 1.1. Use your value of D from A, which was 28 centimeters, and the equation A is equal to 50.0 minus D, so 50.0 minus 28.0, that would give an answer of 22.0 centimeters. Then it requires that we calculate the distance B of the center of the load from the pivot as shown in figure 1.1. Use your value of D from A again, and the equation B is equal to the position of the pivot, which was 47.6 centimeters minus the distance D. So we subtract 28 again, and that would give an answer of 19.6 centimeters. Part C says the student moves the load so that its center is above the 5 centimeter mark and balances the meter rule. He repeats this procedure for the load at 10, 15, 20, and 25 centimeter marks. His results are shown in table 1.1. We are then required in part I to plot a graph of A per centimeter on the y-axis, so we label it against B per centimeter on the x-axis. Now checking the values of A, we can see that it increases by 5 from the bottom to the top, or decreases by 5 from the top to the bottom, and we have the values in B a little bit random. So we can use a scale of 5 on the y-axis if we are not required to start from the origin, and it says you do not have to start from the origin. So you'll just take the first value or the minimum value on the y-axis to be 25 and increase by 5 on the y-axis, so 30, 35, 40, 45. As for the x-axis, we have the maximum number 40.5. We subtract the minimum number 22.5 and we divide by the number of divisions. So we have 1, 2, 3, 4, 5 and a half. So we divide by 5.5. That gives an answer of 3.2727. Then we compare by the acceptable divisions, which is a scale of 1 or 2 or 5. 1 and 2 are not accepted since they are less than the answer. So we will choose a scale of 5, so we will increase by 5. If we started from the origin, we would go 0, 5, 15, 20, 25, and so on. Since the minimum number is 22.5, we will need to start the x-axis from the 20. Then we add 5, 25, 30, 35, 40, 45. Now we will start plotting the points. The first point was at 22.5 on the x-axis, which is at this point, against 25 on the y-axis, so this is the first point. The next point is at 26, which is at this position on the x-axis against 30, so this is the second point. Next point is at 31.5 and 35 on the y-axis, so this is the next point. Then we have 35.2, which is approximately here, against 40 on the y-axis, so this is the next point. And the last point is at 40.5 against 45, so this is the last one. Now we try to connect the first and the last points and see if it gets a best fit line. So all the points which are not on the line are above the line, so this is not a best fit line. So we try another point. So we can try another point starting from the one at the bottom and going through this point here, and then we continue the line upwards. So we have some scattering points below the line and points above the line, so this is a good best fit line. So now I'm gonna use these 2 points. The first one is at the 40 on the y-axis and the other one is at the 25, and we have here 22.5 on the x-axis against 35.2, and we draw 2 lines to indicate the positions of the points. So a vertical line coming down from the top point like this, and a horizontal line from the one at the bottom, just to indicate the points we chose. To determine the gradient in question I, so we had 40 minus 25 on the y-axis divided by 35.2 minus 22.5 on the x-axis. That gives an answer of 1.1811, which we can approximate to 1.2. And since the units for the x-axis and y-axis were both centimeters, so we have no unit for the gradient. And again, if you are drawing this graph, not all students or not all candidates will get the same exact graph, so not the same exact gradient. Part D says calculate the mass m of the meter rule using the equation m is equal to k divided by g minus 1. G was the gradient and k is 25 grams, so we divide 25 by 1.2 minus 1. That gives me an answer of 125, and since this is in grams, so this mass is also in grams. Again, it depends on the value of g that you got in the previous question, so not all candidates will get the same result. Part E says the accuracy of the result obtained by this procedure depends on the meter ruler without a load, balancing with the pivot at the 50 centimeter mark. A student finds that this does not happen. She adds a small piece of modeling clay to one end of the meter ruler to correct it. Suggest if this is a suitable change for this experiment and explain your answer. So in this experiment, we are required to measure the mass of the ruler, so adding a piece of modeling clay to the ruler adds to its mass, so we will get a different mass from the experiment. So no, because this changes the mass of the ruler. So if we had another objective in this experiment, for example, if we are trying to get the mass of a load or a distance, it would not affect the experiment. But since the objective of the experiment is getting the mass of the ruler, it would not help by changing the mass of the ruler. Question 2 says a student investigates a circuit containing different combinations of 3 resistors. She first uses circuit A shown in figure 2.1. So we have 3 resistors connected in series to a power supply, a switch, and an ammeter. Part A says on figure 2.1, draw a voltmeter connected to measure the potential difference V for terminals P and Q. So we connect a voltmeter in parallel, so a circle with a V inside, connected with branches from P to Q. Part B says the student measures the potential difference V for terminals P and Q and measures the current I in the circuit. The meters are shown in figure 2.2 and 2.3. Read and record in the first line of table 2.1 the values V and I shown on the meters in figure 2.2 and 2.3. So we have 10 divisions here between 3 and 4, so each division is 0.1. So the first reading is 3.1. As for the ammeter, we have in the middle here 0.1, and we have 5 divisions between 0.1 and 0.2, so each division is 0.02, so this is 0.12. Part C says circuit B, the student connects the resistors between terminals P and Q as shown in figure 2.4. She measures and records in table 2.1 the values of V and I for this circuit, so 1 resistor in series and 2 in parallel. Circuit C, the student connects the resistors between P and Q again in a different combination, so we have here all 3 resistors in parallel. Part I says calculate and record in table 2.1 a resistance R for each circuit. Use the values of V and I from table 2.1 and the equation R is equal to V divided by I, and add units to the column headings. So we go back. Here in the table, the potential difference is in volts, the current is in amperes, and the resistance is in ohms. Then we divide the values of voltage by the values of current. So if we divide 3.1 by 0.12, we get 25.8333 recurring. If we divide 2.9 by 0.22, we get 13.1818. If we divide 2.6 by 0.86, we get 3.0233. And all the numbers in these columns are to two significant figures, so we are required to have a minimum of two significant figures. That can only happen if we write the bottom number as 3.0. So we have one decimal place in the bottom number, so we write the rest of the values to one decimal place. So the first one would be 25.8, the next would be 13.2. Part DI says calculate a resistance RA, use the value of R from circuit A and the equation RA is equal R divided by 3. So for circuit 1, resistance was equal to 25.8 and we divide that by 3. That would give us an exact value of 8.6 ohms. Then we're required to calculate a resistance RB and use the value of resistance from circuit B. In the equation, RB is equal to R over 1.5. So from circuit B, the resistance was 13.2 and we divide that by 1.5 to get an answer of 8.8 ohms. Then RC is equal to 3 times R, so 3 times the resistance from C was 3.0, and we get 9.0 ohms. Part double I says a student suggests that RA, RB, and RC should all be equal. State whether your results support this suggestion. Justify your statement with reference to the values from the results. So we have 8.6, 8.8, and 9. These are approximately equal, so yes. And we say that the difference is within limits of experimental accuracy. Since the differences between the values are very small, so we assume that they are all the same. Now part E says a student investigates the resistors in circuit A using a variable resistor to change the current in the circuit. In the space below, draw the symbol for a variable resistor. So we have a rectangle with terminals on each side and an arrow that is across the rectangle. Double I says suggest one advantage of using a variable resistor to change the current in the circuit. That would be to be able to have a range of readings, not just one reading. So if we need to plot a graph, we can plot a graph. Question 3 says a student determines the focal length of a converging lens by two methods. We have an illuminated object, a lens in the middle, and a screen on the other end of a bench. Part A says the student sets up the apparatus as shown in figure 3.1. Suggest one precaution that must be taken when setting up the apparatus to ensure accurate measurements. So we can say we have to make sure that the center of the object and lens are on the same level or height. We can also say that we can fix the meter rule to measure distances as close as possible to the equipment, or we can say that we need to make sure that the object, the lens, and the screen are all parallel and vertical. Part B says the student sets the distance U between the illuminated object and the lens to 20.0 centimeters. He places the screen near the lens and moves the screen until a sharp image of the illuminated object is seen on the screen. Describe a technique for obtaining an image that is as sharp as possible. So we move the screen forward and backward until we get the best image on the screen. Now part double I says measure V1, the distance from the lens to the screen on figure 3.1. So using a ruler, we need to measure from the tip of the arrow to the tip of the other end. So this is approximately at the 8 centimeter mark. Since we are using a ruler, we write it as 8.0 centimeters. And it says that figure 3.1 is drawn 1/10 the scale. Calculate V1, the actual distance from the lens to the screen. So we multiply 8.0 times 10. That would give an answer of 80 centimeters. Part C says the shapes of the illuminated object and the image seen on the screen are shown full size in figure 3.2 and figure 3.3. Measure H0, the height of the illuminated object, as shown in figure 3.2. So again, from the tip to the tip of the arrow. This is approximately 1.2 centimeters. Then we are required to measure the height HI of the image on the screen in figure 3.3. So moving the ruler again from the tip to the tip. This is approximately 4.8 centimeters. So we write it down, 4.8. Now part I says calculate the value m of the magnification using the equation m is equal to hi, which was 4.8, divided by h naught, which was 1.2. So dividing 4.8 by 1.2, we get an answer of 4.0. Then part D says calculate a value f1 for the focal length of the lens. Use your values from BII and CII, and the equation f1 is equal to v1, which was 80, divided by m, 4, plus 1. So we divide 80 by 5, that gives an answer of 16 centimeters. Then part E says describe one difficulty that is experienced when using a ruler to measure the height of the image in this experiment. Suggest an improvement to the apparatus to overcome this. So the difficulty is that the ruler would block the light from reaching the screen, and we can fix this by using a thin transparent ruler, or we can use a translucent screen to measure from the back side of the screen, or we can use a screen that has a grid or a ruler scale on it. Part F says the student adjusts the position of the lens so that u is equal to 40.0 centimeters and obtains a new value v2 for the distance between the lens and the screen. Calculate a second value f2 for the focal length of the lens using the equation f2 is equal to u, which is now 40.0, multiplied by v2, 25.1, divided by u plus v2, so 40.0 plus 25.1. That gives an answer of 15.422, which we can approximate to 15.4 centimeters. Since the numbers given were to 3 significant figures, we write the answer to 3 significant figures. Now part G says suggest which value of the focal length f1 or f2 might be more accurate and explain your answer. So if you remember the values for f1, we used the magnification, which used small distances, which are less accurate than using large distances like 40 and 25.1. So we say that f2 is better since the measurements are larger and have less percentage error. So the larger the measurement, you get a smaller percentage error compared to the measurement. Question 4 says a student investigate the effect of insulation on the cooling of a liquid. Plan an experiment which will enable her to investigate how changing the thickness of insulation surrounding a beaker affects the rate of cooling of hot water. So thickness of insulation is the independent variable and the rate of cooling is the dependent variable. The apparatus available includes a glass beaker, a supply of hot water, a lid to fit the beaker, strips of insulation which can be cut to size. So we need to have several layers of insulation to increase or decrease the thickness of insulation around the beaker. And then we need to measure the rate of cooling, but the rate itself, it is a measurement of two quantities, temperature and time. And it says in your plan you are required to list any additional apparatus needed. Explain briefly how to do the experiment, including the measurements to take so that the rate of cooling can be determined. State the key variables that you would keep constant. These are the controlled variables. Draw table or tables with column headings to show how to display the readings. You are not required to enter any readings or values in the table. Explain how to use the readings to reach a conclusion. You may draw a diagram if it helps to explain your plan. Usually it is easier if you draw the equipment, if you can draw it as simply as possible. To just refer to the diagram if you need to write anything. You do not need to write in details if you have already drawn it in the diagram. So here we have a bench and we have a stand to hold the thermometer. So we draw it as a rectangle base with a line moving upwards. That's the stand itself. And we have a beaker to hold the liquid, and we can draw the thermometer as a circle and the line. And we said that we are holding the thermometer using a clamp, which can be drawn as a rectangle, a small rectangle, then held by a boss, which is a small square. And here we have the liquid. We draw the meniscus of the liquid. And it said in the question that we have a lid, so we can use a lid. And the insulation, we can draw it as just a rectangle on each side of the beaker. We can add hashing to the drawing to indicate that these are extra parts, not parts of the beaker. And then we label. So we have here the thermometer, we have a clamp, a stand, the inside part is the beaker, we have a lid, and this is insulation. strip, and inside the beaker we have hot water. So this is the diagram that we need. Now to describe the experiment, we need to say that we will set up the apparatus using different number of strips, but these strips must have a measurable thickness or the same thickness, and we add the thickness by multiplying the number of strips. Then we measure the rate of cooling. First we say that we will need to cut strips of insulation of equal dimensions, and we need to measure the total thickness of the strips, then divide by number of strips to get the average thickness T of one strip. Then we can just say that we would set up the apparatus as shown in the diagram instead of explaining in detail using one of the strips. Then we start to measure the rate of cooling by recording the initial temperature, and we can call it θ1 or T1, and start a stopwatch at the same time. Then we can say that we would need to wait for a specific time and measure the final temperature, or wait for a final temperature and measure the time. For example, I'm gonna say wait for 120 seconds, which is 2 minutes, then record the final temperature θ2, and then we say calculate, not measure, the rate of cooling, and we can name it R, and that is equal to the difference between the temperatures divided by the time, which was 120 seconds. Now basically we've finished the experiment. Now we say that we would repeat all steps for different numbers of insulating strips wrapped around the beaker to get different values of thickness T, but use same amount of water as a controlled variable, initial and room temperatures, and same container. All these are controlled variables. So now we write the table. First we need to start from the independent variable, which was the thickness, which would be expected to be in millimeters. Then we measure the initial temperature in degrees Celsius, the final temperature in degrees Celsius, and we calculated the rate of cooling. So we divided a change in temperature in degrees Celsius and then divided it by the time, which was in seconds, so the unit would be degrees Celsius per second. And then we draw the lines for the table. If you can draw it using a ruler, that would be nicer. And the sections are like this. We only need to write the column headings and units. We do not add anything to the table below the headings. Then to reach a conclusion, we say plot a graph of T per millimeter on the x-axis, since this is the independent variable, against R per degree Celsius per second on the y-axis as a dependent variable to reach a conclusion. So this was the end of the exam. I hope you enjoyed this video and found it useful. Keep practicing, and I will see you in another video.